Hello, everybody. Good morning. Such a beautiful morning to have to be inside, don't you think? I feel like I haven't done this in forever. I guess it has been like 2 weeks, but it feels good. Hello, everybody. Hi, guys. So we are on 9-1 today. I have a feeling you guys are going to like this unit compared to what the unit that we just came from. So that's good. Hello, everybody. So rather than wait, I'm just gonna get right into it because I'm coming to the terms with the fact that a lot of you just come and watch this later, so that's totally fine too. Um, yeah. So so this unit is more geometry, but with some different shapes other than triangles. But you're gonna have to use some of the same logic that you used with triangles. And also some vocabulary. So while I'm going through this, the sort of chart just has like, when we're through with it, all of these little charts will just have like an X or a check mark. But I want you to understand what those check marks are actually saying because you're gonna have to do math with that knowledge later. And so I don't want them to just be like a yes or a no. We need to like actually know what they mean. So really quickly before we even start with the square, which is a good four-sided shape, we're gonna do a little bit of vocab, uh, and then we'll do more as we go. But first of all, those like the top three questions right there, it says bisect, perpendicular, and equal. So just as a review, I feel like you've probably heard the word bisect before, but we have not used it in this class. So bisect means that they cut each other in half. So two lines cut each other in half. So the lengths on either side are going to be the same. Yes, squares are good. Perpendicular, we have used that one. Perpendicular means that they meet at a right angle. Also known as a 90-degree angle. And you know what equal means. That one we don't have to talk about. So that's just a really quick review of some vocabulary, and then we're going to go through each of these and talk about sort of classifying these shapes and what's happening in each of them and what qualifies something to be like a square. So first of all, I kind of drew all over it already, but a square has the definition of a square, which I know is kind of hidden, but this is important. The definition of a square has 4 equal sides and 4 right angles. And then what we're going to do is we're going to talk about the diagonals of this square. So in the square, we're talking about, I'm drawing a little picture to make sure we know what we're talking about in this row of our table. The diagonals are the two lines that go diagonal across the middle of the square. And those two lines in a square, if it's a square, if it meets the definition requirements, they do bisect each other, meaning that those two diagonals cut each other in half. They are also perpendicular, meaning that they create right angles inside of the square. So this angle here is always going to be a right angle in a square. When it says equal on diagonals, we're talking about the length of the two diagonals, and in a square, they are equal. The two diagonals are the same length. We're going to just write that right there. Same length. in a square, sorry if I'm going fast, remember you can pause me. In a square, opposite sides, the sides we're talking about are sides that are across from each other in the square, so either of the two opposite sides, both of them. We're talking about both pairs of opposite sides in a square. And in a square, those two opposite sides are parallel, meaning that if they kept running forever in both directions, they would never cross each other. They are also equal. They're also the same length, the opposite sides in a square. When we're talking about adjacent sides, remember that in triangles we talked about the adjacent side being the one that's next to the angle. Adjacent sides in what I'm saying when I'm saying adjacent is the ones that touch each other. They're next to each other in the square. So there's my little picture with the two adjacent sides in green. So the two sides that are next to each other, are they perpendicular? And the answer is yes, they are perpendicular because of the four right angle thing that squares have. Those have to be perpendicular because they have a right angle. Adjacent sides, the ones that are next to each other, are also of equal length in a square, meaning that that's also a yes. And now we're going to talk about some angles. I don't know if you're seeing a pattern here. So opposite angles being the angles across from each other in the square, so either set of opposite angles. And yes, because of all four sides being, all four angles having to be 90 degrees, they're all four equal. That is also true. The opposite angles in a square are equal. This we're not saying of equal length because length doesn't make sense for angles, but equal size of an angle. Adjacent angles, meaning two angles that are in a row in a triangle, so there's or a square. So there's like a lot of sets of adjacent angles in a square, but no matter which two adjacent angles you're looking at, they are always equal. So a square is kind of our perfect child. It has sort of all of the things, has all green check marks here. And as we keep going, you'll see a lot of those change. A rectangle. The definition of a rectangle is just any shape with four right angles. So we have no qualifications about the side lengths of a rectangle. All it needs is four right angles. So we've sort of plucked that definition point of a square. So the square had four same length sides and four same angles, four right angles. But a rectangle does not have that first part of the definition. Yeah, it just has the four right angles. Sorry, I'm getting distracted by the quietness of the chat here. So feel free, if you are feeling confident about this, you can pause me and try and see if you can figure out if these are all, whether these are check marks or X's. But I'm going to keep going because if you pause me, I'm paused. The diagonals in a rectangle are again the lines that go diagonal through a rectangle. And in a rectangle, they do bisect each other. They do cut each other in half. So the definitions for these things are still the same. The diagonals cut each other in half, meaning that both sides of those two diagonals are the same. Perpendicular. So perpendicular again means that they meet at right angles. So if you imagine for me a rectangle that has like the side length of 60 and then the other side is like 1. It's like a really long and skinny rectangle. The diagonals for that are not going to they're not going to meet at a right angle, right? They're going to be really small angles on the sides and large angles on the top because we've like stretched the rectangle really far. Sometimes it's better to think in extremes because it kind of gives you an idea. But those are not, they're not perpendicular. They do not meet at right angles. They are, however, equal in length. So no matter how long and skinny your rectangle is, or I guess it could be back to a square too, they are definitely equal. So just a note that I would say is that when we say no on something, it doesn't mean not ever. It means not necessarily. So a square is also a rectangle, technically. The definition is just that it has 4 right angles. So a square has 4 right angles and therefore is a rectangle. So sometimes, meaning when it's a square, they do meet at 90-degree angles. The diagonals are perpendicular, but not necessarily, right? So a rectangle doesn't have to. So that's what we're saying when we're saying no, when we're making an X here, we're saying not necessarily. It's possible in some cases, but it's not necessarily true. Opposite sides. Opposite sides are, of course, either pair of the sides where they are across from each other. The first question is, are they parallel? And the answer is yes. Because it's a rectangle and everything is in 90 degrees, they are parallel. The opposite sides run parallel to each other on both sides. They're also equal. The opposite sides have to be equal. The adjacent sides, oops, it's not really a rectangle. I mean, it would have been, but looked more like a square. So the adjacent sides, they definitely are perpendicular. They do meet at a right angle because that's like the entire definition of a rectangle, but they are not necessarily equal. You could have a rectangle with the length of 60 and a height of 1, and that's still a rectangle, so they are not equal. And for opposite angles, meaning any pair of angles that is opposite one another, they are equal because all of the angles in a rectangle are 90 degrees. And same thing for adjacent angles because everything in a rectangle is 90 degrees. So similar in some ways to a square, but some of those things are now not necessarily true. The diagonals are not necessarily perpendicular, and the adjacent sides are like not necessarily equal. Okay. There's these little prompts on the bottom that I think that I will do now. I forgot that these were here, but you can draw 4 other rectangles. So one of my rectangles is going to be a square, one of them is going to be a really long rectangle. Here's a really tall rectangle. We're going to go really extreme here. Here's another rectangle. Of course, those are not perfect drawings, but it's good. And just for completeness sake, why don't we draw 4 other squares? I'm going to draw a really tiny square. There's not a lot of variation that's allowed in a square because all the sides have to be equal. I don't know, do I have room for a giant one? Okay. The only variation you can really have in a square is the size. Because all the sides have to be the same. There's my variety. Uh-oh. Got disconnected from its corner. Okay, let's talk about more 4-sided shapes. Sorry, I have allergies, so I'm sorry that you have to be so close. I know that like you can hear me swallow. It's terrible, but it's better for me to wear these and have the audio be louder than if it's just my computer. It doesn't work as well. Anyhow, a rhombus, the plural of rhombus is rhombi. It's right here. It's kind of like cactus and cacti. Don't ask me why. English is not my major. But that's the truth. Okay, so a rhombus, the definition of a rhombus is essentially like, so um, remember how rectangle has all four angles the same. The square is kind of a rhombus and a rectangle together, and a rhombus has the other piece of the definition. The rhombus has four sides of equal length, but we don't care about the angles. The angles are not important. In a rhombus, they are important, but they're not part of the definition. So any shape that has four sides of equal length counts as a rhombus. So for example, I will just start my drawing of four rhombuses here. One rhombus could be a square um, because having all four of the sides the same makes it a rhombus. Um, but the thing is, other rhombi, ooh, there you go. Other rhombi could be a really squished, like diamond shape. As long as all of the four sides look the same, it's still a rhombus. Um, it could also be, I don't know, a less extreme version, maybe bigger. And maybe I'll draw a just slightly tipped tiny one. There you go. So the angles you can squish are, well, yeah, it's basically just squishing, or like, I guess the word is shearing when you like move it so that it's angled this direction. Anyway, so you can do all sorts of things with the angles, but the sides, as long as the sides are all the same, then you're good. So let's talk about diagonals. In a rhombus, the diagonals are the ones that diagonally cut it, of course. Hopefully you've got that pretty down by now. Um, in a rhombus, they do bisect each other, so that means that the two diagonals cut each other in half. Um, they are also perpendicular. So no matter how like squished they become, even in my little like squished diamond shape down here, the diagonals are going to bisect each other. It's part of what happens when you have four sides the same. Um, so they are always perpendicular. However, they're not necessarily equal. So if you can imagine in this shape, the diagonal that goes across that shape would be much longer than the diagonal that goes just from top to bottom. So they're not necessarily the same length in a rhombus. Um, Opposite sides, being the sides cross from one another, they are parallel. They have to be parallel. Because they are the same distance away in two places, so that makes it parallel. They are also equal because that's part of the definition. All of the sides are equal, so yes, they're equal. Speaking of which, the adjacent sides, the ones that are next to each other, are also equal because that's part of the definition. However, they are not perpendicular because the angles in this shape don't actually matter. They could be any angle you wanted to be. So let's talk about the angles now. Angles, opposite angles being the ones across from each other. The opposite angles in a rhombus, no matter which pair of opposite you pick, are always going to be equal. Because as you will learn, this is also a parallelogram, so rhombuses are like a very specific kind of parallelogram. So opposite sides are always the same. I mean, opposite angles. But adjacent angles, on the other hand, do not necessarily need to be the same. However, they do have some specific properties and maybe we'll talk about them with the parallelogram instead of right now. But adjacent angles, so pairs of adjacent angles will not necessarily, oops, I just drew a check mark. That's not what I meant. Not necessarily be the same. They will be different for the most part, unless it's a square, and then they will be the same. Remember, our not necessarily is what we're saying. We're saying that it's not necessarily the same. And now we come to parallelogram. A parallelogram's definition is just that it has two pairs of parallel sides. So both sides, both opposite sides, are parallel to one another. So we don't care about lengths, we don't care necessarily about angles, we just care that they're parallel, which has some specific effects on the angles in a parallelogram. But first let's talk about its diagonals. Hopefully you figured out what a diagonal is by now. Let me just draw a little picture for consistency's sake. The diagonals in a parallelogram do cut each other in half. They do bisect one another. However, if you think of a very extreme parallelogram with very slanted sides, the diagonals will not cut each other. They will cut each other in half, but they will not meet at a right angle. That only happens when the corners are also right angles. So, not necessarily. Perpendicular, they're not perpendicular, the diagonals, unless, it's a more specific shape. But not necessarily. Also, they're not necessarily equal because the diagonal that goes from the further slanted sides will be longer than the other ones, just kind of like a rhombus. So they're not necessarily equal either. Opposite sides, either pair of opposite sides. It's part of the definition that they have to be parallel. So yes, they are always parallel. And they are also always equal because of the nature of parallel lines and two pairs of them intersecting each other. Make each other equal. Adjacent sides, the ones that touch each other, there's several pairs in the parallelogram, but they are neither perpendicular nor equal. Neither of those things are true necessarily about this shape. Opposite angles. In a parallelogram, opposite angles, so the ones that are across from each other, any pair of them, are always equal. But adjacent angles, the ones that are next to one another, they're not equal. However, for the sake of some math you might have to do, the adjacent angles, the ones that are next to one another, always add to be, they're supplementary. So they add to be 180 degrees. So they are, however, supplementary. Even though they're not equal, they do add to be 180 degrees. So I'm going to draw some parallelograms, some other various parallelograms really quick. Parallelograms are allowed to have pretty much a lot of variation. Here's my long skinny parallelogram. I'm going to draw a really flat parallelogram. And there's one. Parallelograms, technically a rectangle is also a parallelogram because the sides are parallel. So there's my 4 other parallelograms. Quite a lot of variation that can happen there. This next part, I would encourage you to pause me uh, and try these on your own because these are, I think they're kind of fun to sort of think about. And I like to make charts and diagrams. And so this is just like right up my alley. I like to think about which things qualify as which things just according to the definitions. So these are true or false questions. And the first one says, are all rhombi, so all rhombi are parallelograms. So remember that rhombi, the only qualification that they have is that they have four of the same length sides. And parallelograms have two sides that are two pairs of opposite parallel sides. Um, And it's true, actually, all rhombuses, no matter what shape they take, they always happen to be parallel because of the same side thing. Because they all have four of the same sides. So no matter how you squish or try to change a rhombus, it's always going to be a parallelogram as well. It always fits that other definition. So this is a true statement. Um, Second, all squares are rectangles. Yes, that is also true. So squares have an added definition part that says that all four sides have to be the same, but they also include the same definition for a rectangle, which is that all four of its angles have to be 90 degrees. So any square you can imagine in your brain can also qualify as a rectangle. So this is true. The next one is the sort of the reverse of that statement. It says all rectangles are squares. Which is not true. Some rectangles are squares, specifically squares are squares, but not all rectangles, because of course you can come up with a rectangle that is not a square, so that's false. Number 4, all parallelograms are rectangles. If you think back to the definition of a rectangle, it needs to have all four of its angles at 90 degrees. And in a parallelogram, we don't care about that. You can have any sort of angles, and so parallelograms are not necessarily rectangles. Some of them are, specifically the rectangles are rectangles, but not all parallelograms are rectangles. Hi guys. Number 5, some parallelograms are rectangles. Notice the some part. Some parallelograms are rectangles, which is true. There are some parallelograms that count as rectangles. Can you guys hear me? I think everyone else can hear me. Double checking. Yep, yep. I'm making noise. Okay. I don't know what's wrong then. Okay. So yeah, some parallelograms are rectangles. Some of them are. The rectangles are rectangles. Okay. Good. Okay, all squares are rhombuses, rhombi. All squares are rhombi. Remember that square's definition has all four of the sides have to be equal, and so does rhombus. So does the rhombus definition. It says that all four sides have to be the same. So even though squares have the added little bit of having 90 degrees on all of its corners, they do count as rhombuses. So yes, rhombi. Good heavens. It's true. Okay, we're gonna learn 2 more. Hello. Which are, I feel like I put these in order of which ones I like the most. And these last ones are technically not my favorite shapes, but they do have some interesting properties. So a kite, you might imagine, looks like a kite. However, you can't just, it also does have a mathematical definition. A kite has 2 pairs of adjacent equal sides, meaning that are of equal length. indicated by those little slashes on them. And so are these two pairs of sides. And notice that they touch each other. They're not on the opposite side, they're on the same side. Or they're touching each other. They're adjacent to one another. So kites can get kind of, sometimes it's hard for me to identify a kite because the definition is kind of, I don't know. Anyway, but it has two pairs of adjacent equal sides, meaning that two pairs of sides that are the same length and they touch each other. So in a kite, the diagonals do bisect each other. Oh, no, they don't. That's a lie. They do not bisect each other. Even in my really bad picture that I just drew, you can tell that one of the diagonals looks like it's bisected, but the other one has a very long portion and a very short portion. So that is not true. They don't bisect each other necessarily. However, they do meet at 90-degree angles. They are perpendicular. But they are not the same length because it sort of tends to have a long side and a short, like a long diagonal and a short diagonal. Again, not necessarily. It could be equal if it's a very specific kind of kite, but not necessarily. The opposite sides in a kite if you can hear my dog, she's squeaking her toy. Are you? Can't play with you right now. Okay, opposite sides on a kite are definitely not parallel, and they're also not equal. Neither of these things are true. You can tell even from my bad picture that those opposite sides are like definitely not going to be the same or be parallel. Adjacent sides. So here's the tricky thing. In a kite, there's different pairs of adjacent sides. So the pair that I just drew, that's a pair of adjacent sides, but so is this pair and this pair, which one of those pairs are equal and one of those are like, they're not equal. So we're gonna say it's halfway true because only one, actually it's two pairs, isn't it? There's two pairs that work, that are equal, and adjacent, but not all of the pairs, because there are two pairs on both sides that sort of pair them the wrong way, so that they're like, you have a long side and a short side. They are also not perpendicular. That's a big nope, not necessarily. Opposite angles. Okay, wait. Here's a pair of opposite angles. This is also a funky one. Notice this is, okay, this is why I don't love kites. Kites are like, they just throw a wrench in my beautiful little plan. So notice that in my bad drawing, with opposite angles here, there's two pairs of angles that are the same. I mean, one pair. There's two in a pair. So there's one pair of opposite angles that are the same. These two, so in the picture you can tell, like notice that there's little lines right here indicating that those two angles are the same. However, this angle and this angle are not equal. There's a really small angle and a really big angle. So this is only true about one pair of opposite angle. Only one pair. And adjacent angles, none of your adjacent angles are gonna ever be the same. That's a big no. So if you're ever confused about which angles are equal and which aren't, I tried to make these like diagrams really like versatile, I guess the word is. Like no matter what kite you have, the things on the diagram are going to be true. Like the pair of adjacent equal sides and the pair of adjacent equal sides, and also the pair of opposite equal angles. Those are always going to be true um, about a kite. Also, this is always going to be true. The 90-degree angle, because the diagonals are perpendicular. Um, okay. I'm gonna really quickly draw 4 other kites. I'm sorry that this is going way longer than I thought it would, but um, here's a thought. A square, a square counts as a kite because it has 2 pairs of adjacent equal sides. So do rhombuses. Any kind of rhombus also counts as a kite. So that's weird. Here's a really like stretched kite. Oh, that's 4. Okay, we're good. Okay, so here's the thing. Trapezoids, which is our next shape. Trapezoids, there's sort of just a trapezoid, and then there's an isosceles trapezoid. Isosceles trapezoids are way better than trapezoids just a trapezoid because isosceles adds one little qualification that makes our lives a little bit easier. So we're not going to do a whole chart about just trapezoid because they don't have all of the qualifications that we're looking for, and you tend to see isosceles trapezoids more often than just trapezoids. So the definition of just a trapezoid has exactly 1 pair of parallel sides. Literally nothing else has to be true about it besides that 1 pair of parallel sides. So let me tell you all the different, oh my goodness, you can have so many different kinds of shapes as long as 2 of the sides are parallel. It counts. For example, this weird like inverted where both of the sides are tipped the same way, that's a trapezoid. There's parallelograms technically are trapezoids because they have at least 1 pair. They have 2, but they have 1. So like there's just so many variations in a trapezoid because the definition is so sparse, I guess. Technically, like a square is a trapezoid because it has at least 1 pair of parallel sides. So all of those things count as trapezoids because of this common parallel sides happening. Just 1 pair of opposite parallel sides. There's my little arrows to indicate which sides are parallel. Which is why we have this added qualification of an isosceles trapezoid because it has a little bit more specific definition, and therefore it's has more helpful qualities, if that makes sense. So in addition to having 1 pair of parallel sides, so it has 1 pair of parallel sides, the other pair of sides are equal in length. So they are not parallel, but they're equal, which which makes it a little bit easier to work with. This is kind of like the trapezoid that you think of when you think of a trapezoid, is where both of the sides are like the same length and they're the same slope, right? And then they have parallel sides on the top and the bottom. This is like classic trapezoid. However, we call it the isosceles trapezoid because it has sort of that added qualification and we don't have to worry about it getting weird like the trapezoid up above. So first I'm just going to draw a couple of other things that qualify as an isosceles trapezoid. Here's like a little, with a short parallel sides. You could also have really flat, oops, trying to make those the same. Technically a rectangle counts as a trapezoid. for this definition because those two sides are the same and it has one parallel pair of sides. Need one more. I'm just going to draw a really tiny. It looks like exactly the same as the one above. I don't know, whatever. There you go. So notice there's not quite as much variation that can happen in an isosceles trapezoid, which helps us out a little bit. So the diagonals of a trapezoid, I'm not going to draw that because it is right next to its diagonal room. Yes, Nick, you do have a 9-1 homework assignment on MathSpace. It's due on Friday because today is Wednesday. I see you again on Friday. See you again on Friday. So yeah, it's due on Friday. Okay, so the diagonals of a trapezoid, if you can imagine, just looking at the picture, they do not bisect each other. Oops, I almost drew a check mark. They do not do that. They also do not meet at a right angle. Depending on which trapezoid you're looking at, it could be very different angles. And the last one is the only thing that is true, is that the diagonals do happen to be of equal length in a trapezoid. I promise that this is the last shape we're doing, and we're going to do some sort of things that are more like your homework after this, so stay tuned if you want help with that. I also intend to do a study session today. If anybody's interested, I will message everybody, but just FYI. So the opposite sides in a trapezoid, this is throwing a wrench again in my nice little diagram, but the opposite sides, if you can imagine, here's my little picture. There's this pair of opposite sides at the top and the bottom that are clearly not the same length, but there are the other pair of, I should have done that in the opposite colors. This is for you, Becca. Okay, so those two sides are equal, but these two sides are not equal. So one pair, I guess it works either way. One pair of the opposite sides are parallel and one pair are equal. They're not the same pair, it's the other pair. One pair is equal, one pair is parallel. Adjacent sides, pretty much nothing is necessarily true about adjacent sides. Any pair of adjacent sides, they're not perpendicular and they're also definitely not necessarily equal. Like, none of those things are true. For an isosceles, I'm gonna have to draw it over here. Ruining my groove. Okay. Opposite angles in the isosceles parallelogram are like pretty much not ever equal. Depending, I mean, unless it's a rectangle, but this is a no, they're not equal. However, adjacent angles, there's a couple of pairs of adjacent angles that are the same. So like these two angles and these two angles are the same. So again, if you're confused about my like check mark and X thing, especially on these last two, look at the diagram because that will tell you. The angles with like the same amount of tick marks in them are the same. So the upper pair of angles are always equal in an isosceles trapezoid, which is where it gets the name isosceles because the base pair are the same and so are the top pair, the angles. So very much like the isosceles triangle, where two of the sides are the same and the base pair of angles are the same, that's where it gets it. So there are two pairs that are equal, but not all of them, because you could pick a pair of adjacent angles that are not equal. For example, the top, like one of the top and one of the base angles would not be the same. Um, okay. So let's do some actual number work here. This is a rhombus, and I promise you, I know that this is the point where everybody would be like, "Oh, it was so easy before, but now it's terrible." I promise it's actually not this bad on your homework, and you're just using the same logic that we just worked through, except for now there's numbers, and sometimes you have to do a couple of steps. So, uh, here's what we have. The information we have is that this ABCD is a rhombus. If you remember, a rhombus definition means that all of the sides are the same length. It also means it's a parallelogram, hint, hint, because of the angles, the opposite angles being the same. So here's the question. It asks, what is the measure of angle AEB? Remember that this means the measure of angle AEB. So AEB is this angle right here. It's asking what is that angle, and it asks why. So I'm not going to flip back there because I have it right in front of me, and so do you. But if you go back to your rhombus chart, it says that the diagonals are perpendicular, which means that they meet at a 90-degree angle. So the measure of that angle has to be angle AEB. AEB is 90 degrees. Has to be because they are perpendicular. I'm just going to write perpendicular diagonals. Pretty good. The next one asks if the measure of ACD, so I'm not even going to read the rest of the question. I'm first going to like mark that. So the measure of ACD is this whole thing, is 55 degrees. The whole angle, not just like the part in between the diagonal and the edge, it's the whole thing. It asks what is the measure of DCB? DCB. So it's asking, okay, maybe I should have written that somewhere else. This is 55 degrees. Now it's asking what this angle is, question mark. So something that we didn't talk about is that the angles, the diagonals in a rhombus bisect the angles at the corners. You can figure it out. I mean, you can figure that information out by looking at sort of um, the the possibilities, I guess. Each of these little triangles, and I'm gonna erase this in a second. Each of these triangles created in a rhombus are actually the exact same because they have this right angle up here and this side is the same. And we also know that the diagonals bisect each other, so these two are also equal. So each of those triangles are the same, which indicates that the angles have to bisect the corners. The diagonals bisect the angles at the corners of this. So I'm sorry if that was a terrible explanation. It's really hard when there's nobody here and I can't hear your questions. But um, if you need me to explain that differently, you can tell me in the chat. I don't know why my computer is beckoning to me. What? Okay, we're gonna ignore it. So anyway, that all that is to say that that angle that it's looking for, this angle right here, is half of the angle they gave us. So we're gonna say the reason is the diagonal bisects the angle. That might be good to write down in case you might forget that. The diagonal bisects the angle at the corner, therefore its B is 27.5 degrees. Okay, the next question says if the length of CE, which is yes. Okay, I already drew all over that corner, so I'm gonna have to erase it. Sorry. It says this length, CE, is 18 centimeters, and then it's asking for this length down here. Yes, Philip, I know that I'm super late answering that question, but yeah. And this one, with the 18 centimeters being the length of half of that diagonal, hint, hint, half, because those diagonals bisect each other, we know that the other half is going to be 18 as well. So the measure of EB, the length of this is also 18 centimeters. Maybe I'll write right here that what I did there, 55 divided by 2. And the reason I'm gonna put on here is that CE is the same as EB. They're equal because those diagonals bisect each other. And last one, if the measure of CAB, so we're talking about this whole angle here, is 70 degrees, then it's asking what is the measure of CBD? CBD. This one. So here's a thought. We actually already know what that angle is because of, oh, well, we might have changed the information because it says if the measure of CAB is 70. So we're going to ignore what we know already because they could be very different. So here's the thought process we're going to go through. A rhombus is also a parallelogram, and we know something about the adjacent sides of a parallelogram. I'm going to start over again. We know something about adjacent angles in a parallelogram. So if you do not remember, which probably you don't, just flip back 2 pages and look at the parallelogram. We wrote something underneath where it says adjacent angles. We wrote that they are supplementary. The adjacent angles in a parallelogram are supplementary, which means that this 70-degree angle and then this whole angle over here, I'm going to draw it in red, that whole angle are supplementary. So we're going to start with just finding that whole angle, and then we know that that small one is just half of whatever we get. We're just going to take half of what we get. So first of all, I'm going to write down my reasoning. CAB, angle CAB, and angle ABD are supplementary. So that means we're going to just take 70 away from 180, and it gives us 110. And that gives us that whole angle, and remember that those diagonals bisect those corner angles, so we can just divide 110 by 2, and it'll give us 55 degrees. So we then know that CBD, angle CBD, I'm just going to put that here because I don't have room. Angle CBD is 55 degrees. And that would be our answer. So just as a thought, don't get confused by the fact that number 2 and number 4, that information doesn't match. It's because we're changing the size of our rhombus. We're changing rhombuses, basically, in between those 2 questions. We're looking at the same picture, but the picture doesn't have any measurements on it, so we can sort of change the measurements in between 2 questions. So essentially, those questions are not about the same rhombus, if that helps your confusion. So those questions are more like something you'll see on MathSpace. However, MathSpace is usually sticks with like the things you can figure out in one step rather than two. Again, if you're having trouble, please let me know. I haven't heard from a lot of you in a while, so not only will I be just happy to hear from you, but I would be happy to help you. Um, okay, last, we have this beautiful picture of a rectangle. Please do not get freaked out by the weird letters that are occurring in this rectangle. I just used Greek Greek alphabet letters to label the angles so that you could sort of tell the difference between angles and side lengths. You do not have to know how to say any of those things. You just have to like copy what it looks like, especially this one. Like, oh my gosh, what letter? I don't even know. I don't know what, I don't know how you say that. I can't remember, but just learning to write that. I had a class where we used Greek alphabet all the time, and that one was like the one I struggled with. But anyway, don't get freaked out by that because it doesn't matter. We could have just labeled them. Um, uh-oh. I do not know why, Philip. Philip just brought to my attention that we solved for CBD instead of CDB, which would have been a lot easier. So you might notice, okay, so we just solved for the wrong question on this one. That's okay. That one would have been way easier. CDB is this angle up here, which is exactly the same as the one they gave us. Hey, Braxton found beta, capital beta. Anyway, yeah, sorry about that. I did not read that correctly. Those are sometimes hard. Anyway, CDB is just 70 degrees because they're opposite angles and they're the same. That's why. An S as an S sound? I have no idea how to read Greek. No, I don't know. Also, I don't know their names either, so don't ask me. You can always Google them. There's a whole Wikipedia page on the Greek alphabet if you're trying to say their names. I know theta, and this one is lambda. The one that's an upside down Y is lambda, and this is the fish is alpha. The other ones I'm confused. Mm, um, anyway, so these ones, I think that you can do these by yourself. So I would encourage you to maybe pause me and try listing these things yourself. There's not any numbers here. You're just trying to. So the first question says name all of the parallel line segments. So this is a rectangle. So the parallel line segments are here and here. So you just have to write those. I'm gonna do this because it's fun to make the symbols, and also it'll be helpful probably for you to see some of the math symbols again. So AC is a line segment, so you use the little line thing over it. This symbol means parallel. You just draw two parallel vertical lines. It's like an H without a, no, it's not, Philip. It's like an H without a little across thing. AC is parallel to BD, and also CD is parallel to, is it AB? So those are the two pairs of parallel line segments. That's what it's asking for here. The wrong size. It's changing fonts. Okay, number 2 says name all of the congruent pairs of segments. So this one's kind of tricky because there are a lot of them. So again, I would encourage you to pause me if you haven't already, but I'm gonna just start listing them. And the struggle on this one is just getting all of them because there are so many. So AC is equal to BD. These are like the outside segments, line segments. Those are the two pairs of outside, and then there's a whole lot of other ones. Because we have diagonals in there, each diagonal bisects each other. So that means that the diagonals, the half of the diagonals, I guess, are equal to each other. So that's what all of this is. CE is equal to EB is equal to AE is equal to ED. Those are all of the halves of the diagonals. And then the diagonals, the full diagonals are also the same, so that's the last pair of equal sides. Oops, not AB, AD. There we go. And then we come to the fun part where we are doing angles because boy, are there a lot of angles in this picture, and there are a lot that are the same. So I believe the name of this symbol is mu. Ooh, I don't know. It's been a couple months since I've been in college. So that is equal to lambda is equal to gamma question mark is equal to this terrible thing. I don't know what that is. Wait. Oh, that's not quite the same. It needs to go there. There you go. All of those angles are the same. I can't remember what the K one is, and it has nothing to do with the letter K. Those two are equal. I don't know what that one is either. I have no idea. Don't ask me things. I need a Wikipedia before I come on here. Theta, I know that one. And then the one with the tail with the N with a long tail. That's what I'm trying to say. Alpha. And then the Y. I don't know. I keep thinking everything is gamma, but that's not true. Okay, so we have like this. I know this is hard to read, but those are equal. These are different equalities. And then here's the last. Oh no, I didn't mean to get the same color. Pink. There you go. All the right angles. So these angles, because we only labeled the small angles, I'm just using the points instead of the Greek symbols. So even though it's harder, we're being more specific. So ACD is a right angle. So is BAC mu. Yeah. I know the U one. The one that looks like a U with a long tail. Okay, my AirPods are dying. We're on time schedule. C, DB, and DBA. Those are all right angles. And then lastly, though, we're looking for congruent triangles within this beautiful rectangle picture. So as you might imagine, they're pretty easy to see which ones are congruent. There's like the triangle on the bottom and the top inside there, and also the left and right triangles. They're all congruent. So we're gonna just name those. ABE is the same as CED, CED. And then I just drew an A instead of that triangle thing. AEC is the same as BDBE. That's what I meant. Remember that the order of those, like naming triangles, the order doesn't actually matter because as long as you can go in a circle with, anyway. Okay, my technology is dying, so I will get off now. But keep in mind that we're probably gonna do a study session today. Oh, it's because it's been an hour. My goodness, sorry it's been so long. So we're probably going to do a study session at maybe like 11:30, 11:45, or maybe later. So it depends on your interest. I will message you with Google Hangouts. Keep an eye out for that if you need help. Again, there's a homework assignment due Friday. And please let me know if you have questions. Come say hi because I miss you guys and it's depressing. So entertain me because I need it. But anyway, have a good rest of your day. See ya.